I posted that on D2L. I'm hoping by like maybe tomorrow afternoon I will assign homework. I think it's just going to be a shear and moment diagram, a truss, and then maybe something else really similar. Something you've seen before, just a review of some statics related stuff or mechanics and materials or both related stuff. You didn't do trusses in mechanics and materials, right? That's back to statics. And you may have hated them, but we'll do a statically determinate truss just to kind of get you thinking about analysis. We'll learn today where we're actually going to do structural analysis. It's going to be a ways out still, but yeah, I think that's it for kind of announcements. We're just gonna keep going with these notes. So what we were in the middle of talking about right now was, right, we last time we looked at, why are civil engineering structures special, and they're special, right? And then we looked at where this class fits in the overall curriculum if you're on your way to being a structural engineer, and then we started talking about the flow of an engineer, right? I'm really into flow these days. I read a book just recently called Flow. And it was about how flow is like the secret to happiness. Like you're supposed to find something in your life that you flow with, and then you apply that towards like work and stuff. And honestly, it works pretty well, right? That's one of the reasons why I really enjoy snowboarding as much as I do, because I flow, right? You just flow. You're just like carving and skiing, just carving nothing, or mountain biking, same thing. And then you take that, you're supposed to apply it to life too, right? Like when you're working on your homework and so that's why we have a couple topics to start with flow. The flow of a structural engineer, right? You start out with the architectural drawings, you do some preliminary calcs, you determine the loads on the structure, then you determine how those loads affect the structure. This is kind of the structural analysis component. We'll discuss load paths and things like that in there. And then designing the structural elements based off of these loads, right? You can take those loads, it goes into these elements, and then we'll design the structure, right? It has to meet strength and stiffness requirements. It has to be stable. It has to be serviceable, right? You have to be able to use the building afterwards. And then you have to make it inexpensive, right? You have to make it barely stand up. I think we talked about that before, right? That's one of the strengths of being a structural engineer, or one of the purposes of being a structural engineer is you want to make it as strong as it needs to be, but not stronger. Because we want to make it efficient and affordable for the buyer and whatnot, or the client. Okay, and then there's iterations. You might get through all of this stuff, and then you're like, oh my God, this is going to cost a lot of money, right? And it's too expensive to use steel. Or steel prices change, right? This whole process from here to here can take up to a year, right? And then by the time you get done with it, you're like, oh my God, steel prices skyrocketing. They did just recently skyrocket, by the way, during the pandemic and stuff. They shot up. And then now they're on their way back down. And so things may change, right? Or just say, oh, the client changed their mind or something like that. And so then you got to go back up here and change certain aspects of this, all of it or some of it or whatever, and you just keep going around until you finalize what it is that you're going to do. Okay, that's under the iterations. But you're not done yet, right? Because then it goes into construction. And then after this, we'll do construction drawings. Let's see, what did I do? These all one thing? Oh, yeah. Structural drawings. Right, this has changed over the years, these structural drawings, right? There's this thing called BIM now. You guys have heard of that before, is that correct? Building Informational Management. There's classes on it. I highly recommend you take that sometime, right? Because when you go into the real world, there's a lot of people in the real world that don't know how to use BIM, and if you really want to make yourself valuable and hireable, if you come in saying like, oh yeah, I've taken 2 classes on building informational management or 1 class, they'll be like, great, we need somebody that can do that, right? Because when I went through school, I used CAD, computer aided design. Turns out I was also a state champion AutoCAD drawer in high school. I don't know if you don't know, you probably didn't even know you could be a state champion. I was, right? But they had that, but I don't know how to use BIM, right? I'm too old to know how to do it. And there's a lot of people out there that in the same situation. They know how to use CAD, but they don't know how to use BIM. It's super cool. It's really cool. Maybe we'll have somebody come in and give us a demonstration of it sometime. But it's really cool, because when you make drawings, you have plan views, and you have elevation views, and you have cross sections, and you have all these things on it. If you use BIM, like, you just have to make the change in one place, and it updates all of your other, like, your cross views there. It's really cool. It's a really neat thing. But anyways, that's under structural drawings. You go iterations, and then you have to provide structural drawings or modeling, right? Or modeling in BIM, right? Building information management. I think eventually, though, like what you hand to the contractor is like blueprints. And a lot of contractors don't use building information management, so you actually have to hand them your classic, blueprints and stuff like that. But anyways, that's one of the last steps. There's still, even after that, once you make those last drawings, EFGH, you're still involved. It's called construction administration. CA sometimes is what you'll hear it called. You're actually part of this process as well. You're part of the construction administration, right? Part of this, what we have to do is this thing called shop drawings. Right? When I was an undergrad, I did get a job as an intern at a structures firm for, my dad worked there, but he hooked me up. And I worked at Morrison and Merrily. And I didn't really know. I'm probably similar to you guys. I had just gone through Structures 1, and then I got hired, completely unqualified, but thanks to my dad, I got the job. And then I went and worked there, and one of the very first things they had me do was shop drawings. And so if you guys get an internship, which honestly I think you might be qualified after this class, the very basics in structural engineering you'll know, and you can get a job doing. And one of the first things you might do is shop drawings. And what it is when you get done with your modeling and your drawings, you say this is how we want the structure to look, and then it goes off to the manufacturer, the fabricator, the steel fabricator, and they say, all right, given your drawings, this is what I think I need to make on my end, the steel side, and then this is what I'm going to provide you. And then someone has to go back and make sure that what the engineer said was going to happen and what the fabricator, steel fabricator, can provide you are the same thing. And so you have to do that. You check it. You open up the structural drawings, you open up the steel drawings, and you just compare them and literally just play a matching game and make sure that they match the whole way down. It's super boring. Interns end up doing it, but that is part of the structural engineer's job, is to check the shop drawings, right? And you have to go back and I would probably say check shop drawings. Right, you have to check the shop drawings. And so I just want you to think of me. If you are doing this, if you find yourself in your career at some point checking shop drawings, just remember, like Barry told me about that. This sucks. It sucks. But it's a job, right? It's one of your first things that you'll be able to do. There's these things called requests for information. They're called RFIs. Right? So if the contractor's in the middle of constructing something, they're like, oh, it says you need to connect the column down to here. It says you need to use 5 bolts. We can't get 5 bolts in. We can only get 4 bolts in. Is that okay if we only use 4 bolts? We can only use 4 bolts that are slightly bigger than the size that you requested for the 5 bolts. Is it okay for me using 4 bolts instead of 5 bolts? Right? That just a little simple thing like that. If the contractor's doing it right, they will make sure that it's okay with the structural engineer first. Or like, I couldn't find that size of beam, I can only find this other size of beam, it's a little bit bigger, is that okay if I use that? Or it's a little bit smaller, is it okay? That's called request for information. The contractor submits them to the structural engineer, they double check it, and then they respond to that request for information, either yes or no, or sometimes it involves additional tasks of calculating things. The other thing happens is they mess up in construction a lot, and then they put columns in wrong places and things like that, and you have to come back and say, oh, is that okay or not? I'm gonna try to do guest lectures, right, with like real structural engineers. There's this former student of mine, Sam. She was the lead engineer on this, the new gym, right? And she said that is just a total clusterfuck. There's so many requests for information that are involved in that project. And she said, I would love to come in and talk to you about what contractors should not do. And that's part of as a structural engineer, you have to do that. Okay, requests for information. RFIs, right? Sometimes they have site visit, right? Site visits and structural observations. There's kind of documenting whether or not people are if they are building it the way that they're supposed to, and you just kind of go in and check to make sure everything that's happening. Related to that, there's also a thing called special inspections. They're both kind of tied to the same thing. You just want to go in and make sure that you said, this is how I want the structure designed. Someone has to double check that they're actually building it the way that you said that they should build it, right? Because really, if there's no observation from the structural engineer perspective, who knows what those crooked contractors are going to do, right? If they, right? I mean, seriously though, right? If nobody's watching them, then they might just like crank out some shit that they're not supposed to be doing, and so we have to keep an eye on them, and that's kind of site visits and structural observations. Just every once in a while, popping in and making sure they're supposed to be doing things that we're supposed to be doing. The other thing, these special inspections are fancier. So sometimes, like in the code, we'll get into this later on, but sometimes in the code it'll say, hey, a moment frame would be an example. If you're gonna design a moment frame, we'll talk about those shortly. You're gonna design a moment frame, and if you do it a certain way, like a special way that's gonna be a really ductile failure, so it has lots of warning, it's gonna dissipate you get rewarded by the code. They say, well, if you're gonna be really careful and design this building in a real special way, we're going to let you design for less loads, and you can use smaller members for that. But you promised that you were going to design it a certain way. And the code isn't just going to take your word for it. So they have this thing called special inspection. And actually, it comes outside the structural engineer. If you design the building, you don't do this. It has to be a third party. They come in and they double check that you're doing what it is that they said they're doing because you got rewarded already. So we'll get into that. That's special inspections. That you go in and say, yes, they did it. Somebody else, a third party, comes in and says, yes, they did what they said they were going to do. And then they were justified in getting their reward and using less loads. Okay. And that's kind of where it would end at that point, right? You go through all these steps and you end up with construction administration, and you're dealing with that. And then eventually the building is complete and you walk away. Right, which is nice. And then after that, there's your job as a structural engineer still, you may get called back on an existing structure if there's extra cracks or things like that are around there. One thing I want to point out that's really sick, is that a word you guys use? Fire. It's really fire, it's really lit, is the fact that what's really cool about structural engineering from my generation is the fact that, like, look, you spend all this time going through all of these steps, right? And it's your job. One job, like this building across the street here, right? That's a perfect example. Between when it was originally designed and got constructed, it's supposed to open up this spring break. We'll see if it happens or not. That whole process is several years, right? So several years of your life is spent going through all of this stuff. Obviously you have other projects going on, but you spend blood, sweat, and tears on this. When you're done with this, there's something there afterwards, right? There's a building there afterwards, right? What do? You go through environmental, you have a poop plant. And even that, the poop and pee plant, that's not you. You didn't design the poop and pee plant. You designed the process that needs to be implemented in the poop and pee plant. Technically, the structural engineer is the one that made the structure so that it's there, right? This building just celebrated its 100-year anniversary, right? Roberts Hall, 100 years. So some engineer, long gone, designed that structure, and then spent his life doing that, and then handed it off, and then they built it, and then it sits there as like a monument to their work forever, right? The structural engineering in civil, that's the only one that has that, right? We're the only ones that have monuments after our, right? Think of that thing, right? That's pretty cool, right? I'm very biased towards structural engineering, just in case. And I apologize. If you like environmental engineering, I apologize. You're stupid, but I apologize. Geotech, I guess, obviously the structure has to sit on something, so, we need the geotechs for everything to sit on, right? So their monument is buried underneath the ground that the structure is sitting on. Not as cool, right? So, you're catching my point. The structure is just, it's cool shit. While we're there, so let me show you. So this is kind of just walk you through. This is something. So this is we'll talk about code sets or drawing sets later, right? As we get into it. But this is an example. These are hundreds of pages long, by the way. The drawings. This is what you as a layperson would call like a blueprint, right? So these things. We'll look at them in a second. I think this thing is like 300 pages long. It has. This plan set has the architectural drawings in it. It has the mechanical drawings in it. It has the structural drawings in it. It has like all sorts of, basically the whole circuit. This was all made in BIM, this particular project. This is the dining hall. The new dining hall. Not Miller Dining Hall, but the other one, right? The one, it's new to me. It's probably been there since you've been here, but like the one over here, right in front of Montana Hall. But so this is the architectural drawings, right? So the architect comes in and says, all right, this happens before you're even involved typically, right? All this is kind of, we gotta have a kitchen over here, and we gotta have this, everything right here, and we need to have walls. This is the overall dimensions. We kind of want the walls to look like this. We have to have corridors like this. We need all this stuff. They come up with that. And at this point, this is what I talk about. You get involved after this, or at least the general footprint of the building is actually decided at that point. Then you get called in. You're like, okay, make it stand up now. This is what we want. Make it stand up. They don't know at this point how big the foundation walls need to be and the footings underneath it. They don't know, like, where am I going to put the columns? Where am I going to put the beams? Where am I going to put the, all that stuff. That's where you come in, right? They don't know what the lateral system is. And so this is, so you come in and you're like, okay, yeah, I'm going to do some preliminary calcs. I'm going to see where it is. And then I'm going to decide, like, what my floor plan is going to look like, based on which way I'm going to have my columns, layout, how am I going to have my beams, how am I going to have my girders, where are my joists going to be. You come in, and then, so that's where you get started. Then your product is this. So this is the same floor plan. This is a different sheet, right? The other one here was A102. That means the architectural plans, page 102, right? Where the structure comes in, right? It's S, in this particular one, S201. So this is the structural drawing. So you have an architectural drawing and you have a structural drawing. And so based on that, right, after we do all my calcs, this is what the structural drawing would look like, right? It tells you, we're going to have these big girders that are going like this, and we're going to have these beams feeding into these girders, right? And then that would be your product. The structural drawings would look like that, right? And we'll spend more time looking at these on occasions, right? So what we're going to do in this class is kind of take off from, say we met with the architect and they said, here, this is what we want. These are the general, floor plans of what they're going to be. And then we're going to talk about, like, where do we come up with, like, what are the loads that are going to be on this beam, and what are the loads going to be on the girder that's going across, and things like that, right? So that's where we're going to kind of focus. That's what, actually the next topic is the flow of this class. Like, how are we going to handle? How are we going to get to a point where we can be given that and then have this as an output here? Right. Before that, though, I want to show you some pictures. So here's a plan set. Oh, what do I got here? So this is the new, let's see, go back to the top. Oh, this is norm structural drawings. You can see how many pages is this. They're very complicated. Obviously, it's going to take a while before you get to a point. These are all just the structural drawings. 91 pages. The structural drawings are 91 pages long, right? Could you generate this with hand drawings? No, right? This is CAD. This is BIM. These things are product. These are a product of using BIM, right? You gotta see. I mean, all structural stuff, right? And so they have, they tell you where this is the foundation drawings, right? They tell you what the footings are gonna look like underneath. Underneath it, they're telling you what it looks like. There's like a footing wall that's going around the outside of this thing, right? And then they have little You guys ever seen blueprints before? Somewhere? In one of your, like 101 or something like that, or just in general you saw it in life? In a class you saw them? Construction practice, you talked about it. So they have these things, and what they do is they do cross sections every once in a while, right? So if you're like, oh my God, I'm looking at this, I don't really know what's happening, and so then every once in a while you'll see a cut, and then you can go look up what the cross section is going to look like, and just to give you a better idea, let's see if we can find a cross section or something. Did you see some? It might be too long to find one, but anyways, 91 pages long just for the structural drawings. There is another package, the architectural drawings, and there's another packet that's the mechanical drawings for the HVAC system and things like that. Let me show you. This is pretty cool. These are Robert Hall drawings. These are sick, right? This is 100 years ago, right? Before CAD, this is 28 pages long for the mechanical and the structural drawings all together. All hand drawn, including, look at that son of a bitch, right? If you're in front of Roberts Hall, next time you walk in there, by the way, I only go in the front doors of Roberts Hall. I never go in through Cobley. You should adopt this. It's like, if you go in the front doors of Roberts Hall, you got like these engineering emblems and a big thing on top says College of Engineering, and then it's like your heart is lifted because it's a 100-year-old engineering building. versus like going in Cobley, like we said, your soul leaves your body. Like at least it's happy for a short period of time. It's way more regal. It's more prestigious to go in the front of Roberts. Even if it's a pain in the ass and it takes you longer, do it. Just go around, go to Roberts. But you're gonna walk by this hand drawn, right? Made of terracotta. I don't even know what that is. I think it's expensive, right? I think it's up with the Yellowstone Club a lot, right? I tell you, I don't have terracotta on my house. Right? I've heard that they built. There was two buildings that were supposed to be made at the same time. There's this one and there's one over here, and they both have the exact same floor plan. And they built Roberts first, and they spent all the money on Roberts, and then the other building over here. You look at it, you'll see it. It looks just like Roberts, but it has none of this. I bet it doesn't have terracotta, right? It does not have terracotta involved because they spent all the money on Roberts Hall. It is really cool. It's a cool structure. I all hand draw stuff, but you could see, right? Every cross section is hand drawn, right? Your profession is, back in the day was different, right? Look at the columns. Right, those big pillars that are out front, they put a little cross section of it. They do that. Isn't that cool? They did a celebration last year. Look at this.
Where did you find these for Roberts?
They did a celebration last year because it was 100 years old, and then Tim White and I knew it. It was me. I was like, hey, guess what? Roberts Hall is the 100-year anniversary, and then I was expecting like a big barbecue with hamburgers and stuff. It was like they held it on a Saturday, and like nobody came, but there was a celebration because it was a Saturday. And anyways, I tracked them down. The university had them in like an archive someplace, and then we said, can we get a copy of it? They were in really weird paper. We have the originals in our offices right now. Tim's got a couple of them hanging up, the originals hanging up on his wall and stuff. But it's pretty cool, right? They had all those these things in there. But you can see, look at that. I don't even know how you would go about drawing. Look at that. Look at that. Dude, when I was in school, as an undergrad or in high school, we did a CAD class. We did computer aided design, but then also had to do hand drawing. Did you guys have to do hand drawing too? Yeah. Super useful. I use it all the time. You can tell by how good my handwriting is how useful it is. But I mean, they don't teach you this stuff, right? Look at that. You ever noticed in Roberts when you walk up the stairs, right on the first floor, the stairs are divoted? 100 years of students dragging their feet going up the first flight of stairs. Look at it next time you go down. I just noticed on Romney here, same thing. Especially the first floor because there's most traffic. There's little divots from students over the years walking up there. Anyways, they're way more complex now, but I just wanted to show you historically how cool they are. And be glad the trusses, right? This is before they had real like I-beams and stuff like that, so everything was riveted. So if you needed a bigger section, you took a bunch of plates and you rivet them together. And so this is what the trusses look like up there, all riveted. It's actually a concrete moment frame is what it is. Some of the floor plans and stuff. Let me show you something else here. Actually, go back here. Drawings. Let me see dining hall. I want to see how many pages. Volume 1 is 93 pages long. Volume 2 is 106 pages. So 200 pages of structural and architectural drawings on the MSU dining hall versus 28 total for all of Roberts. But these are pretty cool. That's not. This is the construction of Roberts Hall. It's pretty interesting. Like, look at the pulleys and shit, right? And these guys standing up there. You can see like it was a different time. Look at this. Model T out front, right? This is the era, right? This is the era of the time. Right? Look around. Look at around Bozeman there. Isn't that crazy? It's historic. One of the reasons why I wanted to be over here. I want to be in a historic building. Walls. It survived it. It's made through a couple of earthquakes. There's a big earthquake. The one that made Quake Lake. This was around when that big earthquake was. It handled it. Roberts made it. Honestly, I think I'd trust Roberts more than I would Cobley. So I'm right between the two. That's where my office is, and it's like, which way should I run? I think my instinct, I'm headed towards Roberts. It's more regal. If I'm gonna die, if I'm gonna die, I want to die in Roberts Hall. Yeah. I honestly think that it's a national conspiracy. Every building on every university across the United States, every engineering building is the worst and most poorly designed buildings on campus. And then there's going to be an earthquake, and then they're setting it up that all the engineering students die in an earthquake. And then it just is like they're aiming for the coincidence or anyways. I think it's a conspiracy. I think they're trying to kill us all off with an earthquake stuff. What's the word? It's ironic that all of the structural engineers die in an earthquake, but all the other buildings are fine. Anyways, look at the casting of concrete, right? Now you got those big boom trucks, right? That have the pump trucks that you've seen those before. That's their pump. You ever seen the big crane that comes out and then there's a spout on the end? That's a concrete truck. It's a pump truck, and so they dump concrete into the back of it and then they pump it out into place, and that's how they place it. Even residential they use that. But again, just look at the houses and surrounding part of Bozeman there. My favorite is digging the foundation. So here's those trusses we just saw the drawings for, all riveted together. This is digging the foundation. He literally is doing it with a shovel, right? A shovel and a mule and a plow, right? No hydraulics, right? No backhoes and stuff like that, right? It was just let's get a couple of horses and a plow and let's dig this son of a bitch out, right? Different era. Yeah, there's the finished. Look at those houses in the background. Basically a shanty town, right? Is that what you call that? Built in 1923. This is in Romney. Flip through. I found these today. This is in Romney, right here. So this is out in that gym down there. We're up on the running track. Is where we're at right now. That's right. There's that running track, and then actually, it was more than a running track. It's also a stadium, right? Because this is where the Bobcats played, right? The basketball team played in this gymnasium right here, and so they had the stands up around the outside, and then this is some sort of, it looks like a Ku Klux Klan meeting. Some sort of pointed hat. That Ku Klux Klan meeting in the 1940s. Right. Oh, looks like another one. Another Klan meeting in the 40s. I don't know what the pointy hats are. I believe that one's a funeral. They had a funeral here for one of the Hamilton. It was Hamilton. It was Hamilton Hall. It was he was the president here, I guess, and he died. They had his funeral in the gymnasium. There's a floor system in Romney. So this is Romney under construction right here. When we get done with this class and you go to take the FE and then you're supposed to have covered certain things and then you're like, well, I don't know that, but I did see some historical photos and I did watch Milena fight in Mortal Kombat, but it was a good time. It was a good time. So there it is, the foundation of it again. I just like to see the surrounding area. There's is that the steam plant? Same steam plant that they used to heat everything. Again, there's the construction of on the outside. Basketball game taking place in there. I think we won a national championship in 1929. I think that's correct, yeah? Golden Bobcats is what they called them. Are you aware of this? Yeah. Yeah. So I think that was it was that one, the caption was something about that. One thing that absolutely drives me fucking crazy about MSU's campus right now is back in the day, 1923, because I think they built that same time. 1922 maybe is when they built Romney. How the fuck didn't they line it up with Montana Hall? Doesn't it drive you crazy? Like there was nothing else around. Like here it's very evident, right? This is coming out straight. It comes into the side. Like how fucking hard is it to line? Is the other building on campus just line it up so that the sidewalk it drives me bonkers. I can't walk down that without noticing that. I'm a little upset. I always walk down I walk. Yeah. Anyways, always line up. If I'm walking that way, I'll line myself up with Montana Hall, and if I'm walking this way, I'll line myself up with Romney Hall. But I'm never in the middle of the sidewalk. You have to be off to the sides in order to do that. It drives me crazy. But also, I come, I'm coming down here. I also will never cut across this way because I want to walk in. I come in this way just because it's regal. Because you're not gonna come in the side door wrong. I'm coming right down the middle. I'm gonna walk right to it. Another basketball game. That's pretty cool, right? Where we're at gymnastics. And it's all by itself. There's some more construction photos. It took a long time before we were able to get back into this building. This building was really dilapidated. Dilapidated. You sure?
I'm just guessing. That sounds,
You guys don't know either, right? I used to get really self-conscious when I was like spelling and my drawings in front of you guys. You guys are just as bad as I am. There's a few in there. Like, you don't know the difference between dated and dated. Like, you don't know, right? So it's okay. I should just be more confident and be like, it is dated. But it was really dilapidated. But we tried getting into it and stuff, and all the windows were broken out and stuff for years. And then we kept asking the state, please, just let us fucking remodel this thing. And they were like, no, it'd be cheaper to build a new one, right? And they were like, tear it out and build a new one. And they were like, it would be cheaper. It would be way cheaper to do that. But it's historic, right? And we're like, no, it's historic. And they're like, no, you're going to get a new one. And they're like, no, we want the old one. No, we get a new one. It took many cycles in the legislature, and then finally they approved the money for it, right? Yeah. And a lot of people complain about like the fanciness of our buildings and stuff. Like, you may hear it sometimes. Like the state, you'll hear somebody that's not somebody in the society or community. They'll be like, "Oh my God! Like, look at you! Like Norm Asbjornson Hall! Like, what a waste of taxpayers' money." That's not taxpayers' money, right? That is Norm Asbjornson gave us $50 million. We built that. So you just stand up for us, right? They'll say the same thing about your new gym. I guarantee there's an article in the paper about, or an opinion in the paper about how MSU is wasting money. So that's not state dollars either. You guys are paying for those gyms. Well, you didn't vote on it. Your predecessors voted on it, right? Like, they said, yes, we want to spend our money, and we're going to have a facilities fee or something like that, and so you reap, and then you're not even going to reap the benefits of it, right? You guys are actually, it's opens in the spring, so you'll get a year or two out of it. It'll be sweet. But so that's also not their money either. So stand on, that's not your money. This building, though, it is their money. This is theirs. This is theirs. It's the state of Montana gave us the money for that one. There it is, a close-up view of the. Does not appear to be QuickBooks. It appears to be interesting hats. I don't know why, but it was the style back then, maybe. Pull-ups. Oh, there you go. There's the one under construction there. Pretty cool. I'm gonna see if we get a tour of the roof. You go. I've done this before. Like up in here, up in these rafters. There's a way you can get up into the rafters. And we can go up and inspect this. Have you been up there before?
Yeah.
Do you tour in a class or something?
Yeah. It's like our freshman year.
Okay.
Right when it was open, they let us.
Yeah, let's go up there. Let's go up there. See what we can do. We might as well do that instead of learn the stuff we're supposed to. Okay. All right. Let's get back to this. All right. Let's talk about the flow of the course. How are we handling this?
It is dilapidated.
Dilapidated. It is officially, it's confirmed, dilapidated. This is how I spent a lot of time, a lot of soul seeking about how I wanted to present this class. I think I got it, right? So this is how I currently envision it. We're going to dive in. We'll see if we stick with it, but I think as of right now, this is how I want to do it, right? I think one thing that we really pride ourselves in our department is making you, is marketing you as a practicing, we're trying to make you into practicing engineers, right? When I went to the University of Washington and I did my master's and PhD there, I didn't come out knowing how to be a structural engineer. If you said, "Hey, Mike, you need to be a structural engineer now," I'd be like, "Oh God." I'd be really. I'd be pretty worried, right? Because they focused on how do you become a person that's really good at researching structural engineering. Like I know that I could derive, like in your steel manual, which we'll get to eventually, I could derive all of those equations that govern like the design of these things. If you said, can you use them to actually design something? Nope. But if you design something, I could really dive in and check that it's okay, right? So we really pride ourselves on our product, you guys being like a practicing engineer. So that's how I'm going to focus on this. Is like how, if you were going to be a practicing engineer, how would you do this? Also, I hope that when you get done with this class, you would be marketable as an intern this summer even to do shop drawings, load paths, things like that. You won't be able to design anything, but you'll have like the basics of the design. You can come up with the loads and things like that. So that's how I'm going to try to focus. I'm going to be a practice engineer. At the University of Washington, I tracked down some notes from there. They did the whole entire class structural analysis. Not once did they talk about loads, dead loads, live loads, wind loads, seismic loads. They didn't even talk about that. It was just all analysis. As an academic, that's where I would like to go, right? Like I really like matrices and stiffness methods and I love that. But I would be doing you guys a disservice by doing that. So we're gonna approach this, and I looked into fundamentals engineering, like what they expect you to know, and they do expect you to know some things about the loads and where they're coming from, and that's what the approach I'm gonna take. Also related to this, just one more push for structural engineering. Daily, probably daily, at least weekly, I get an email from somebody of one of the structural engineering communities in Montana, and more likely in Bozeman, saying, oh my God, do you have interns? Oh my God, do you have graduating structural engineers? Since I've been at MSU almost 20 years now, I have, I believe, really close, except for the Bartley brothers, 100% placement in a structural engineering firm in Montana or elsewhere in the United States, right? We just had a student go to Boston. He's a structural engineer in Boston right now, right? And he was sought after and stuff like that. So it is a push. If you want it, especially if you get a master's, if you want to be a structural engineer, man, there's jobs waiting for you. And there's a high demand for them across the state and across the country at this point, right? So there you go. For reals though, literally, like if you were like, oh, anyways. They're fighting over you right now because they're like, well, I really want an intern. And I was like, dude, I got nobody. Everybody's already taken right now. And they're like, and then they're like trying to poach the students from different people and stuff. If I said, oh, I got somebody, they're going to be good eventually. Maybe not right now, but they can do the basics. And I was like, get them then. Get them when they're in structures, right after structures 1. And then you just hold on to them as they go through grad school. And then a lot of times a lot of our students work part-time while they're going to school as well. All right. And that's a couple different ways of funding grad school. We'll talk later. Okay. Yeah, okay. What did you learn in structural? Well, I learned that structural engineering was really cool. I didn't know how to do it, but we're going to talk about the general structural systems and behavior. I'm just going to introduce them, right? You've heard trusses and things like that, but we're going to really systematically define those things to begin with, right? What are the I guess I should write it off. Might as well do this, right? Types of elements. Right? What are the structural elements? Columns and beams and walls and plates and things like that. So we're going to talk about the different types. That's what we're going to start out with, right? Just so you've seen these types of structural elements. We're going to talk about gravity systems and lateral systems. You have gravity loads you have to resist, and you have lateral systems. We're going to define those things, what we mean by those two systems. I'm going to talk about load paths. Maybe not, and actually, in fact, not in this order. Actually, let me do the order here. How about as well, while I'm here. Types of elements, structural systems, gravity lateral systems, and load paths. Yep, that's it. Okay, that's what we're going to start out with that. Just a basic understanding of what the heck we're talking about here. Then we're going to talk about structural loads. Right? We're going to talk about types of loads. Right? You guys heard of dead loads and live loads? You did. So where did you hear that before? I mean, just from me? who told you that? But never in a class, or not in statics. Briefly? Okay. Yeah, and there's dead loads and live loads, and there's uncertainties associated. We really know a good thing about dead loads, how much something weighs, right? But then live loads is who knows, right? And so there's anyway, so we'll talk about those in detail. Dead loads and live loads, the different types of loads. In here too, load combinations. We'll probably have to touch on design philosophies. Right? There's this thing called ASD versus LRFD, and there's two different design philosophies, and they involve different factors associated with dead loads and live loads and these load combinations. But we'll touch a little bit on that. All right, gravity. Yeah, we'll talk about that. Weight. That is basically what it is, right? The weight of things. And then lateral systems will, wind and earthquake. Right, we'll dive into each one of those things. And these are defined to us, right? This is, we'll put that in there. ASC 7. Actually, I think we're going to do ASC 716. That's the current code. Right? That's where these all get defined, is ASC 716. We'll just define these structural loads. Oh, I'm going to add one more thing here. I'm going to say tributary. Not tributary. You ever heard the word tributary area before? You guys ever talked about that? Like what you have in statics, maybe? Oh, you did. Okay, yeah. So you're like, how much load does a particular beam carry, right? Like, what is going to affect that load, right? Or what's going to affect that beam? What parts of the load, and how do you get that load into that element and simplifications and stuff like that? So that'll probably be underneath that section as well. C, it'll be structural analysis. I would assume where I kind of envision an exam happening around here-ish. Okay, kind of like, as of now, I'm kind of splitting the class into two, like the first part being, systems of behavior and structural loads, and then getting into structural analysis as an additional part. Okay, so what do you do with these things, right? So this is going to be determine moments, shears, deflections, right? Needed for design. Right? We can't do design. Design is structures too, but they are we need these things: moments, shears, and deflections in order to design. Structures 2 will be over here in the design, but we'll talk about where we get those things from. Okay, we're going to probably start out with beams. Right? We'll revisit shear and moment diagrams, so they're a big part of this. Yes, Madison. Yeah.
Regarding testing, is that going to be like 2 tests, so midterm and final, or?
I don't know yet. I think in the syllabus, I said 2 midterms because that's what Audrey did before me. And then, but now, as like I've laid it out, it seems more of a natural 2. I don't know. I think honestly, right now, if you put a gun to my head and said, "Tell me what we're gonna do," okay, I would say we're gonna do a midterm here, then a final-ish or another midterm, and then a project at the end. It's how I envision it right now. Probably, but maybe not. Your guess is as good as mine, Madison. That's how I envision it. I like the idea of a project at the end, where we say, here's this big structure, right? Put it into a computer program and do some analysis and come up with moments and shears. God, I talk a lot. We were supposed to be way farther today, right? Okay. Right, but let's finish it. We've only done 1 page of notes, right? Determine moments, shears, deflections, here, beams, and then trusses. All right, trusses. We're going to do right? Conventional matrix method, maybe more on the matrix method. Again, this is my vision. This is my vision, right? And then we'll do frames. Right? That's gonna be matrix. Right? And then I guess maybe we'll do D here. I had a professor once that would always abbreviate analysis as anal. And it was made it really funny. It made it really funny, but I'm just like, oh my god. If he was completely clueless that he was doing it, right? Might as well. Maybe I'll pick that up myself and keep things interesting. Structural anal software. Okay, just abbreviate that for us as we go along. Okay, so because this, right, it's important to understand like how do you analyze a beam and how do you analyze trusses and how do you analyze frames, right? And we're gonna I need to do it because FE makes you do it, right? So we're gonna have to. I am gonna cover the things that FE wants you to know, but then also, you know, as an academic, I gotta make you do some matrix methods as well, right? Because that's cool. That's what really attracted to me in structural engineering, was doing the complex analyses. And so we'll do those things along the way, because it's actually really cool when we apply to trusses. We'll probably only get through trusses, applying it, and then I'll probably show you how it gets applied to frames and stuff. And then if you go on to do grad school, they spend a lot more time on it's the foundation of finite element analysis, if you've ever heard of that. It's the foundation of it, is in this matrix method stuff. But that's kind of where I see it. And then I'm gonna say, hey, let's just use software, right? Because in software, you draw a picture of what you think the structure is going to look like, and then you apply the loads, and then it does it. Behind the scenes, it's doing matrix stuff, and it's handling that stuff for you. And that's just the beauty of these matrices, is that it is designed for a computer to do it, and we're going to have a computer do it, right? And well, it's really cool. Like, you know, when we have all these load combinations and different types of loads, the structural analysis software handles that stuff for you. Right? You define your dead loads and your live loads, and you go through and you say run, and it'll go through and it'll calculate like all the different combinations and keep track of the worst case loads and all that stuff for you as you go along. I'm going to show you how to use that and kind of set you up for it. We're supposed to be way beyond this. Well, so this is where we'll start on Friday, right? We'll start talking about structural systems of behavior, right? We'll define what beams are and columns and tension members are, and then beam columns and then plates and then walls and stuff like that. We'll kind of define those elements, and we'll talk about the different systems as well. Okay. Break. Stay tuned for a homework sometime in the next couple of days.